everybody. So today we are going to talk about an experiment for mirrors and lenses, and this is something that we covered just some time ago. So just to do a review, if you have lens, today we are going to talk about only the converging lens, because that's the ones that they will create a real image that we can actually show it to you. Virtual images we cannot show it to you because it is something in the mind of the observer, and we cannot catch that. So here's the first thing we are going to do. Look at a converging lens. As you can see in here, focal point, center of the curvature on this side, focal point, center of the curvature on the other side, and AB is our object, which is basically, you are going to see it's just an arrow. And then, like always, we need only two rays to follow and see where they intercept. So here's the red one, parallel to the axis. I draw it this way so they can very quickly produce the image. Parallel to the axis, and it's going to refract, and it's going to pass through the focal point on the other side. And the other ray is the one that goes through the focal point on this side, and it's going to comes out parallel to the axis on the other side. They intercept each other at point A prime. This is the image of A, and the rest is going to follow the same process. And so the image of AB becomes A prime, B prime, and we are going to see that actually during experiment. As far as the equations are concerned, the equation for lenses and mirrors are the same. 1 over s plus 1 over s prime is equal to 1 over the focal distance. And the second equation that I have written in here is the lateral magnification that shows the ratio of y prime, which is the size of the image, to y, which is the size of the object, shown right in here. That's the definition of the lateral magnification. And as I have explained for you during the lecture time, excuse me, this ratio becomes the same as the ratio of s prime, which is the position of the image to the optical device, which in this case is the lens, divided by the position of the object to that optical device. So this is the equation that we are going to use, or you are going to use, to derive all your analyses. And this is the diagram for lens. For mirror, again, we have two types of mirror, as you know. We have concave mirror and convex mirror. We are not going to show you any image on convex mirror because there is no image. It's all virtual. But concave mirrors, they will produce a real image. And I've only shown one condition. The same way that I've only shown one condition in here, and that is when the object is further away from the lens than the center of the curvature. As the object comes closer, you will see that the image is going to go away and become larger and larger as the object comes closer to the lens. Same is going to happen right here in concave mirrors. I have just one scenario that I'm showing you. I put the object AB on the other side of the center of a curvature of the mirror, and the image is going to form between the focal point and the center of the curvature, obviously on the same side, because nothing passes through the mirror, obviously. So once again, we are going to get two rays. One I choose to be parallel to the axis that will will reflect from the surface of the mirror, and it's going to go to the focal point and continue. That's this black ray. And the other one, I'm passing through the focal point, reflects from the mirror, and it's going to reflect back to the parallel to the axis. These two are going to intercept each other at this point, and that point becomes the image of this point, A prime, image of A. And the rest of the points in here are going to also follow along this line. So A prime, B prime, which is I've drawn in green, is going to be the image of AB. Equations, as I said, is the same, right? Right here. and lateral magnification is also going to be the same. The first part of the experiment, we have set it up in here with Mariana, and you can see we have the source of light, then we have a cylindrical lens in here to basically focus the light which is coming from the source to this screen. The screen in here is simply a window with openings in it, and that will create a bunch of parallel rays. So the parallel rays are going to come in here. Here is one very simple concave mirror on this side, convex mirror on the other side, as you can see, like that. And we put the concave part in here, and a situation will happen, which I have drawn on the board in here, right there. So this is our concave mirror. The parallel rays are coming in here, and they're going to reflect. And the property of the cylindrical mirrors, or a spherical mirror, I'm sorry, spherical mirrors, is that that if the coming rays are parallel, they are going to all focus at a point, which is, we call it the focal point. Okay, so they're all going to go like this. And we have pictures that we have taken from this scenario, and your job is to basically find what is the focal distance of this mirror. Let me see if it says right on it. Well, it doesn't say what is the focal distance, but you can figure it out by just looking at the drawing that you will see later on. If I turn it around and put the convex mirror towards that incoming parallel rays, of course the rays are going to diverge. So I'm going to quickly show that in here. So this is the convex mirror, and these parallel rays are coming towards it, like so. And they are going to diverge after reflection. So you will see something, scenario like that. And of course they will not intercept each other, so you will not get a real image ever. But we can see this trace because we take picture of these rays of light, and you're going to have that. So what you need to do is to extrapolate these rays in here, the reflected rays, extrapolate them, and if you do it neatly, which I didn't, they are going to all intercept each other somewhere in here. These are actually just the extrapolation of the actual rays. This is behind the mirror. And so this point in here, which you can measure on your paper, becomes the virtual focal point of this convex mirror. That's basically it for now, and the rest of it, we are going to actually do the experiment, and hopefully we get the images which are visible enough so you can measure things from it. The other thing that I have to show you right now is how you present your results. There is a table in the last page of your manual that is basically this, and what you need to do is, for every scenario that we create, you gotta find, this is first for lens, and then you do the same exact table for mirrors. So you put your object at so many millimeter distant from the mirror, or from the lens in this case. Okay, that's your S, the distance between the object to the optical device, which is going to be our lens, 500 millimeter. And then you measure the rest of these. So the rest of this must be filled by you. You find where is the location of the image, how large is the height of the image, and then this just calculation. Once you have these, you can calculate this. Then from this equation that I showed you earlier, right in here, you can find basically you're finding this part in here, but 1 over f is the reciprocal of the focal distance of the lens that we are going to use. And so this is given. That's your raw data that is given to you, but this is what you are going to basically calculate. If everything is ideal, this number must be the same as this number because of this equation. Of course, it won't be because of the errors in measurement and so forth. So there is a discrepancy between this value and this value, which you are going to calculate later. And the other thing that you need to measure is the ratio of y prime over y. And you have that because you found this. And you're going to give you how high is the size of the object. So you can find this. So that's measurement. And also you have these two numbers, s prime and s. And you can find this value in here. So this value in here and this value. And again, ideally, these two must be the same because of this equation that I told you. And you are going to see that they won't. And you're going to talk about the difference between these two, which involves the error of measurement. That's basically it for lens, and then you do exact same thing for the concave mirror.